Welcome to the recording of 6.3 logarithmic functions. Part A is about the basics. Here I have the graph of y equals e to the x. We can draw the graph of y equals its inverse function by taking the line y equals x and reflect the original graph. This inverse function is denoted by ln x. You can also read it natural log of x or log base e of x. So this is the inverse function of e to the x. You can do the same thing with a different base. Log base 10 of x is the inverse function of 10 to the x. In general, if you have b bigger than 1, then log base b of x is the inverse function of b to the x. Now let's look at this question. We're given that natural log of 5 is equal to x, and we want to compute or we want to check which one of these is true. So first, write down what we know. We know natural log of 5 is equal to x. We also know that e to the x is the inverse function of natural log of x. So I can write e to the natural log of 5 equals e to the x. And because e to the x and the natural log of x are inverse functions, this value is equal to 5. So I have 5 is equal to e to the x. If instead of e, I have a different base, so here this is called a base, and this is equal to some number x, so this is called exponent. Writing this down is equivalent to saying that the base to the exponent is equal to what I have in front of log base b. So think about base to the exponent equals what's inside of log base b, and then your exponent should go on the other side of the log. Next, we want to know what log base b of x times y is equal to. You can either remember this or you can go through what I am about to do if you don't remember. So first, it's hard to just go directly from here, but it's easier to work with exponential functions. So let's first turn this into something that looks like an exponential function. So first write down log base b of x is equal to some number m. This would mean that b to the m is equal to x. And do the same thing for log base b of y. Set that equal to some number n or some letter n, and this means that b to the n is equal to y. Then I have x times y is equal to b to the m times b to the n. And this is the same as b to the m plus n. So I have xy is equal to b to the m plus n. This means that log base, the base b of what I have here, xy, is equal to the exponent m plus n. So this means that log base b xy is equal to log base bx from here plus n, but n is equal to log base by. And so these two are equal. Again, you can either remember this or go through what I just did if you forget. Here's another logarithm rule. You can either remember this or you can go through what I'm about to do. So we have this log base b of x to the r, and r is inside of the parenthesis. So in general, this here, where r is outside, is not going to be equal to what we have. So we know it's not going to be a, and in fact, this is b. But if you're not sure, let's go through the steps. So again, I'm interested in this value here. So I set this to be some letter. Let me call it a. So then from the definition, I have the base to the exponent is equal to what's inside of the log, so x to the r. And because I'm trying to check, is this really equal to this one? I need log base b of x. So I write down log base b of x equal to some letter n. And so I have the base to the exponent equals what's inside of the log. And now I want to work with these at first. So I have b to the m is x, and b to the a is x to the r. So this means b to the m to the r is equal to x to the r. And so this is equal to b to a. The first equation is just replacing x with b to the m, and the second equation is replacing b to the a with x to the r. And so I have that because of these equality, so I have b to the rm equals b of a. They have the same base, so the exponent have to be equal. So r times m is equal to a. So I have r times m, but m is log base b of x, and a is log base b of x to the r. So these two are equal. Previously, we saw that if the base is equal to e, then we have that the derivative of b to the x is equal to itself. So now let's compute the derivative of b to the x when the base b is not equal to e. And we're going to use a technique that will appear often in this class. So first we write down y equals the function that we are interested in differentiating. And then we will take the natural log for both sides. So ln y, ln b to the x. And from the previous slide, we see that we can bring down this exponent x because it is inside of the parentheses. Next, I want to take advantage of the fact that natural log is the inverse of the exponential function e to the x. So I take e to both sides. So I have e to the natural log of y equals e to the x times natural log of b. And this becomes y. And this becomes just the same thing, but let me first write down the natural log of b first, times x. And now realize that natural log of b is just a constant. So now we know how to differentiate this using chain rule. Next, I will differentiate both sides. So I have dy dx equals e to this constant, natural log of b times x. And then I have to multiply with the derivative of this part. So I have natural log of b. Now, this here is just b to the x times the natural log of b. The reason this is equal to b to the x is because we know that y is equal to this quantity. So this quantity here is equal to y, but then y is equal to b to the x. And so the derivative of b to the x is natural log of b times b to the x. So for example, if my b is 5, so like I have 5 to the x, the derivative is natural log of 5 times 5 to the x. And if the base is, say, e squared, then again, using the formula, I have natural log of e squared times e to the, so e squared to the x. And we can simplify this if we want. This is the same as 2 times natural log of e times e to the 2x, but natural log of e is 1. So 2 times e to the 2x is the derivative of this function. And that makes sense because we could also compute this using chain rule and get the same thing. In part B, we will say a few words about the graphs and growth of logarithmic functions. Like I mentioned earlier, you can sketch the graph of log base b of x by first sketching the graph of b to the x. So if b is bigger than 1, you will have a picture that looks like this for b to the x. And your log base b of x would look like this. So the reflection across the line y equals x. For example, let me work with the base 5. So the domain of log base 5 of x would be values. So all numbers that are positive. So as you can see from this picture, you can only have x values from the right side of the origin, this way. You can write this as the interval 0 to infinity. You can also write all positive numbers. And then the image of a function is all of the possible outputs. In the book, this is called range. So range and image mean the same thing, but usually outside of this textbook, most books will use the word image. So in your future classes, you'll see the word image. So I want you to get used to it. So we'll usually use the word image. So the image is the set of all possible outputs, and the set of possible outputs are actually all of the numbers. So the y value of this graph can be as low as you want, and can also be as high as you want. So this would be the interval of all numbers. You can also write this R, or you can write all numbers or all real numbers. The exponential function b to the x grows fast when b is bigger than 1. And the larger the base is, the faster it grows. For example, 5 to the x grows faster than e to the x and 2 to the x. Their inverse functions, the logarithmic functions, are the opposite. If your b is bigger than 1, then larger base means slower growth. So here, log base 2 of x grows faster than log base 10 of x. So larger b means slower growth. Now let's talk about asymptotes. If b is bigger than 1, then you can actually make log b of x be as big as you want, given a large enough x. And so to denote what I just said, you would write the infinity symbol. This means that there is no horizontal asymptote. So there is no such line that would bound the value of log base b of x. You can also consider the value of log base b of x as x approaches 0 from the right. And as you can see from the graph, the closer the graph gets to the y-axis, the larger it gets in the negative direction. And you can make this value be as large and negative as you want by choosing x that is sufficiently close to 0. We denote this by writing negative infinity symbol. Next, I want to talk about how the logarithmic function grows very slowly. This is something that we will talk about later in this class, but I want to give you a quick taste of it. I want to compare the natural log with the square root function. So here I have a table of a few values of the graph y equals square root of x and y equals natural log. So at first, when the value for x is not very big, the two graphs grow at similar rates. But eventually, as your x gets really large, we see that the square root function grows much faster than the natural log. So looking at this, it is possible to compare the growth of the two functions by looking at their ratio. So I take the ratio of natural log of x over the square root. And looking at this graph, it looks like this limit should be 0, because eventually the natural log is much slower than the square root. So as x gets large, we would expect this ratio to go to 0. And in fact, that is true. And we will learn how to compute this in section 6.8 using calculus, as well as computing similar types of situations for other functions. In the next section, we will learn about derivatives of logarithmic functions and also how to use them to evaluate integrals.